So, so we'll come back again. We continue from where we stopped in the previous part. In the previous part of the lecture, we talked about keyless approach, the concept. We explained the concept. We explained some of the enabling techniques. Now we will talk about the merits and demerits of this approach, the keyless-based approach or the signal-to-interference noise ratio approach, where we need to have a better signal-to-interference noise ratio at POP than that at Eve. And we can do that, we can have that naturally due to the channel conditions, due to having POP to be closer to the base station than Eve, or being in a position or location where the channel condition is better, whether at the small scale level or large scale level. And now we need to just explain and discuss briefly the merits, the main merits, of course. There might be other extra merits, but here we are just mentioning the five major ones. And obviously, as anyone can think, uh, uh, this approach, a SINAR-based approach, doesn't require sharing secret keys. And this is an advantage. This is a merit. Why we consider it to be a merit? Why do we consider it to be an advantage? Is because we don't need algorithms and methods and ways to deploy in our network to share the keys securely, because this is a cumbersome, hectic, tedious process, not easy to do, and especially when you have large number of users in the network. Now, in physical security based on a SINR, which is the keyless approach, doesn't require having a mechanism to share keys securely between the transmitter and receiver, which is a good advantage. The second advantage is this approach can practically achieve perfect secrecy. Yes, you hear it right. This approach is one of the very rare approaches that can, for the first time ever in the history of security and information security, that it can achieve perfect secrecy, which means regardless regardless of the computational power that Eve might have, Eve will not be able to decode the message correctly, successfully. You can reach to that strength of security. Why? Because you are securing here at the signal level and you are securing at the signal to interference noise ratio. If you come up with a way, with a technique, with a method that can ensure having bad SINR at Eve and good SINR at POP, in this case, you can achieve what's called perfect secrecy, where the signal to interference noise ratio at POP will be way more than Eve, and Eve will be close to zero in this case, and the communication rate will be almost equal to the secrecy rate in this case. This is related to the second advantage, and the third advantage is this category can make sure that most processing can be done at the transmitter side only, without having the receiver to do anything. This most processing is done at the transmitter side. Why do we consider this to be an advantage? Anybody can guess. The reason why we consider this to be an advantage is because this is good for Internet of Thing devices. So imagine I have a tiny device, Internet of Thing, and I want to transmit secure data to it. Right now, if I want to use encryption and decryption, the Internet of Thing has to deal with public key, private key, has to deal with shared common key, and so on. Okay? In this case, this will add complexity. Complexity will add latency and delay and more consumption in power. And all these things are bad for an Internet of Things device, because they consume its resources and drain the battery quickly. And instead of making it live for 10 years because of using complicated encryption to provide security, you are reducing the lifespan of your Internet of Things device, which is bad for the network, bad for the device, and costly in terms of money. You need, instead of using just one device within a certain period, within a certain time duration, you need to replace the device maybe more frequently and more often, and this will cost money. But thanks to physical layer security, you could deploy a security technique that doesn't require the receiver to do anything at his side. All what need to be done can be executed and processed at the transmitter, which is Alice, and send the signal over the air. And by the time the signal reaches Eve, it will degrade its performance. It will not be decodable. But when it reaches the legitimate receiver, because the signal is optimized to that receiver's channel, the receiver will be able to decode the data successfully. That's related to the importance of having multi-processing at the transmitter side. This is good not just for Internet of Things application, but also for cellular, for 3GPP cellular mobile standards. Why this is good? Because when you come up with a new technique and a new method, and the implementation of this method is at the network side, so this can be a big motivation for companies to adopt such a solution. Why? Because changing things at the network side is easier than changing things at the receiver side. If you want to deploy now, let's say users, they have phones and they are using them. And let's assume somebody came up with a novel technique, a novel physical layer security technique that can provide ultimate security, but we need to change something in the chip of the device, something in the modem of the device. So what's the solution? We need to ask all the users, all the clients to buy this new device, this new modem, this new device with a new modem that got this feature implemented inside it. Of course, this is difficult to do in a market, in any market. Asking users to get rid of their phones and buy new phones to just deploy this feature doesn't make sense. And whenever you need to deploy a new feature, you need to ask them to buy a new phone. This is really hectic and unrealistic. But if they deploy this feature at the network side, at the base station, where the telecom company or the IT company can do that conveniently, and regardless of the type of the phone in the hands of the users, the data can be received securely, then all what they need to do is just maybe a simple update or a simple notification that right now you let the mobile device know that you don't need to do anything to get your data securely. You just need to tune to this frequency, and everything will be fine. All the processing will be done at the transmitter. So this is good if from different perspective and really useful. Now, what's the fourth advantage here? This approach, called a SINR-based or keyless approach, can enhance POP's performance besides providing security. Yes, it's true. The main goal was to enhance security, to improve security, to have a much more confidential transmission using a much more, I don't want to say sophisticated techniques, but rather a much more intelligent techniques, because they don't depend on using complex math or complex arithmetic in order to provide security, but on the fact that the SINR at POP should be better than the SINR at Eve. That's the main concept. But while you are trying to improve, as we know, the equation of security here, SINR at POP should be better than SINR at Eve. So if you do anything to improve POP's SINR, you are basically improving the security. And if you do anything to improve the security based on adaptation based on the channel, you are also basically improving the performance of POP, improving its reliability. So when you adjust, for example, when you optimize your diversity techniques, let's say space diversity, to provide security, you are also essentially improving the bit error rate of POP. So let's say we have this bit error rate figure, and here in the x-axis we have signal to interference noise ratio, and here we have bit error rate in the bucket, bit error rate or bucket error rate, whatever. But this is on the y-axis. This represents the number of errors. And let's say before adaptation it was something like that. After adaptation it was something like that. Before adaptation. After adaptation, after employing our technique, the bit error rate improved. So as you can see, if we draw a line like this, we can clearly see that at a lower S sin R, we can get the same bit error rate. Or at the same bit error rate, or at the same S sin R, we can show that our technique can provide better bit error rate than the previous one. So which one is better, this curve or this curve in terms of bit error rate? The upper one or the lower one? The lower one is better because the lower one says at lower signal to noise ratio values, here, lower signal to noise ratio values, I can get what? Lower bit error rate, which is good. Lower bit error rate means your packets are received mostly successfully without any problems, without any interference, without any noise. You don't need to retransmit them again. But the other way around is more difficult. Okay, so what about the fifth advantage here? What's the fifth advantage? The fifth advantage says that this category can work in both FDD and TDD system. We need to explain that, of course. I mean, what do we mean by FDD? What do we mean by TDD? And why does it work in both of them? You mean there are other categories that don't work in both of them? And why? So these type of questions that you may be asked in the exam, maybe in the final. So why do we need FDD? Why do we need FDD and TDD first? And why are they different? And how this method can work in both FDD and TDD. Now let's explain this in this way. FDD stands for frequency division duplex, TDD time division duplex. In this case, in the TDD, the uplink and downlink between the transmitter and receiver happens at the same frequency, but different times. But in the FDD, frequency division duplex, in the uplink, it's at a certain frequency, in the downlink at a different frequency. That's why they are different. So when the uplink at a certain frequency, when the uplink at a different frequency, so we said TDD has the same frequency, but FDD, the uplink is F1, let's say, the downlink is F2. Now, since the frequency has changed, we have different frequency. So in this case, what happens, because we have different frequencies, we will get different channels. And because we do have different channels, the channel with respect to E is different from the channel with respect to Bob. And in this case, we cannot exploit the reciprocity feature of the channel in order to provide physical layer security. But for these techniques, some of the adaptation techniques, especially the adaptation techniques that we optimize based on Bob's performance, usually they work on FDD and TDD, not just TDD. In physical layer security in general, we prefer to have TDD systems, but this helps us, FDD helps us to in terms of delay in the network and separate the uplink from the downlink, and in terms of removing and mitigating interference issues in the network. But if we want to provide security for it, we can select always the SINR based category, which can provide security even in FDD systems. So these are the merits, and we can discuss after that the demerits of this approach called SINR based physical air security techniques. Any questions so far?